Okay, then looking at page 12, just to recap, so far we've looked at the ideal Carnot cycle. We then moved on to modify the Carnot cycle into the Rankine cycle, which was more representative of the actual steam power cycle. And then there was a variation to the Rankine cycle, which was the superheated Rankine cycle. And as we discussed before, there were some marked effects, improvements in terms of the performance of the cycle by using superheated steam at entry to the turbine. There was an increase in the cycle efficiency, and it also avoided or reduced at least the problems that could possibly occur by having too low a dryness fraction as the vapor leaves the turbine. And as we said, if it dropped below 0.88, then the liquid droplets in the steam as they're making their way through the exit of the turbine can have a detrimental effect on the blades of the turbine. What we're going to do in this section is we're going to begin where we left off in the last section with the superheated steam Rankine cycle, and we're going to modify it further. Now some of the reasons for that is again to increase the cycle performance, cycle efficiency, and specific steam consumption, and also to try and eradicate and not just reduce the likelihood of water droplets causing damage to the turbine blades. If we look at the first variation at the bottom of page 13, we have the reheat cycle. So we have a temperature entropy diagram here that is showing the plot, or it's actually superimposing two cycle plots at different pressures. Very often it's desirable for us to increase the pressure in the boiler, but as you can see from if you look at P dash, obviously that is a higher pressure than P. And when you look at the dotted line, which is the expansion through the turbine, at the higher pressure P dash, you'll see that at exit from the turbine, the dryness fraction is lower than it would be at the lower pressure of P. Now, as we mentioned, we want to avoid a low dryness fraction at exit from the turbine. So we need to find a way to be able to employ a higher pressure in the boiler, but at the same time avoid an undesirably low dryness fraction at exit from the turbine. And one way to achieve that is to employ the reheat cycle. The cycle in terms of the layout of the plant is shown in figure 7a on page 14. So really what it is, we have at exit from the boiler at point 2 our saturated steam. Once it leaves the boiler, it comes into the bank of superheating tubes. So it comes out at point 3 superheated, which is what we looked at the end of the last section. So the difference here is there is now an additional bank of tubes, which are reheater tubes. So RH means reheat. So this time expansion is carried out in two stages. We have a high pressure turbine, HP for high pressure, and we have a low pressure turbine, LP for low pressure. So we have the initial expansion from 3 to 4. At exit from that point, the working fluid is fed back into the boiler and through this additional bank of reheater tubes. And very often Obviously we have a lower pressure now than we did have at point 3 because there's been some expansion in the high pressure turbine. But very often when the working fluid is fed into the reheater tubes, it's taken back up to the same temperature as it was at point 3, but at a lower pressure. So the working fluid is then fed back into a lower pressure turbine, and expansion, the second stage expansion, takes place from point 5 to point 6. And then, as normal, the working fluid is fed into the condenser where more heat is removed until we have our liquid condensate at point 7, and it's then fed into the feed pump, and the cycle continues. So if you look at the temperature enthalpy diagram, and you can do this, if you printed off your notes, you can do this while glancing at the figure 7a. So at point 8, the working fluid has left the feed pump and it's fed into the boiler. So from point 8 through to point 3, so that includes the initial change from our liquid condensate at point 8 through to saturation point here, and then through to the superheated condition at point 3. So this includes the bank of superheater tubes that you can see in figure 7a. So we've gone from our liquid to saturated liquid to dry saturated vapor, and then out to superheated vapor here at point 3. So in other words, the total heat received by the working fluid in the boiler is going to be our enthalpy at point 3 minus our enthalpy at point 8. So 3 to 4 then, we have our isentropic expansion, the vertical line from 3 to 4 dash. We have our actual expansion, assuming that we have an isentropic efficiency of less than 100%, from 3 to 4. So 4 is the actual condition at exit from the first stage of expansion from the high pressure turbine. At this point, it's fed back into the boiler, into the reheater tubes, where at a lower pressure, it's taken back up to the same, in this case, the same temperature as it was at point 3. And then we have the second stage expansion from 5 to 6 dash for isentropic and 5 to 6 for actual. And as you can see, point 6 is just inside the line of our dry saturated vapor, meaning that we have a high dryness fraction, which is what we're after, and is what the reheater cycle achieves. So from point 6 over to saturated liquid at point 7, we have the condensing process. And then from 7 to 8 dash, we have our ideal feed pump, and 7 to 8 actual. And then the process just continues again. So we have this, the difference from what we looked at before in the last section to this one is that we have this two-stage expansion in the turbines, high pressure, low pressure. So as before, we can plot these lines, these two vertical lines, on our enthalpy charts to find out the ideal enthalpy at point 4 dash and point 6 dash. We can then apply our equations for isentropic efficiency to find out what the actual enthalpies are at point 4 and point 6. And in terms of finding out point enthalpy 8, then we just employ the equations that we derived in the pumping section in an earlier part of the notes. Point 3 as well as point 5 can either be found from our tables or simply read from the enthalpy chart. At the top of the next page, we have our equation for the cycle efficiency, which again we're employing our standard equation of net work over the heat received. And again, remember, net work is the work output from the turbine, in this case turbines, minus the work input to the feed pump. And the heat received is the total heat received in the boiler, which includes the heat received in the reheater bank of tubes. So putting that into changes in enthalpy, net work, we have H3 minus H4, which is the enthalpy drop in the high pressure section of the turbine. We also have the work done by the low pressure turbine, H5 minus H6. So that is the work output, if you like, H3 minus H4 plus H5 minus H6. And then we have the the work input to the feed pump, which is H8 minus H7. And the heat received is the total heat received in the boiler and superheater first of all, and then the reheater tubes. So again, with reference to the diagram in figure 7a, then we have H3 minus H8, which is the total heat received until the exit of the superheater tubes, and then we have the heat received in the reheater tubes, which is H5 minus H4, and that will give us our cycle efficiency. If we take a look at a worked example on the reheat cycle, example 2 here says, calculate the cycle efficiency and the specific steam consumption for a reheat cycle that's operating between an upper pressure of 100 bar and a condenser pressure of 0.04 bar and a superheat temperature of 450 degrees Celsius. It tells us that the intermediate pressure of the steam is 8 bar. That is the pressure of the steam at exit from the high pressure turbine. It tells us that the steam is expanded to saturation point and is then reheated to the original superheat temperature. So in other words, from point 3, the actual condition of the vapor as it leaves the high pressure turbine is going to be dry saturated, which is shown on your TS diagram, which you can just see here. So then it goes back into the reheater, into the boiler in the reheater bank of tubes, and it's taken back up to the original superheat temperature of 450 degrees Celsius. So it says take the turbine and feed pump efficiencies as 80%, that's for both turbines, and 72% respectively. And it says, it asks also, what is the condition of the steam at exit from the low pressure turbine? In other words, what is the dryness fraction? So if we establish first of all the pressures at the different points in the cycle. Now we have 3 pressures. We have the upper pressure at exit from the boiler, that is the pressure at point 2 and point 3. And if you remember, that pressure is achieved in the feed pump. So the job of the feed pump, as well as circulating the working fluid around, is to provide the pressure at the boiler and therefore input to the first turbine, which means that the pressure at point 2 and point 3 as well as point 8 is going to be the same at our upper pressure of 100 bar. So the feed pump gives us our 100 bar. The steam is raised at constant pressure, therefore pressure 2 and pressure 3 are going to be the same. That pressure changes as the vapor is expanded in the high pressure turbine. So we have a drop in pressure, and the question told us that the intermediate pressure, that is the pressure between the 2 turbine stages, was 8 bar, which means that P4 and P5 are 8 bar, because again the working fluid is receiving heat at constant pressure. So we have P4 equals P5, which is 8 bar. After the low pressure turbine, we're down to condenser pressure, which we were told in the question was 0.04 bar, which means that P6 equals P7, So again, heat is rejected now at constant pressure. So P6 and P7 are both at a lower pressure of 0.04 bar. In terms of temperature, we were told that the superheat temperature and the reheat temperature were both 450 degrees Celsius. So T3 and T5 are both 450 degrees Celsius. Our next task is to evaluate the enthalpies at different points in the cycle. Now, to do this, it's going to be a combination of using the steam tables and using the enthalpy chart. If you look at the different points in the cycle on the TS diagram, in terms of being able to find enthalpies from the tables, we know the pressure and we know the temperature at point 3 and point 5, which means that these two enthalpies can be read from the tables. We're going to be plotting these on the chart as well, so they can be read from the chart, but they can be simply read from the tables, and we can always cross-check to make sure that we are plotting the expansion in the turbine correctly on the chart. You may find the tables slightly more accurate than using the chart, but there's always a little bit of interpretation in terms of using the chart. So we're told that the pressure and the temperature at point 3 was 100 bar and 450 degrees Celsius. So if we go to our steam tables and we go to the superheat steam tables and we find 100 bar and then the column for 450 degrees Celsius, we'll see that the enthalpy is 3241 kilojoules per kilogram. At point 5, we were told that the pressure was 8 bar, and we're told also that we're back to our original superheat temperature of 450. So again, in the superheat steam section in the tables, if we find 8 bar and the column for 450 degrees Celsius, we'll see that the enthalpy is 3373 kilojoules per kilogram. Looking around the cycle, you can see that point 7 is on the saturated liquid line. Now we know that the pressure at that point in the cycle is at our lower pressure, our condenser pressure of 0.04 bar, and it's on the liquid line, which means that we're looking at HF. So to get H7, then we look at our saturated water and steam section in the property tables, find our pressure of 0.04 bar, and then read across until we come to our HF column, and you'll see that the enthalpy there is 121 kilojoules per kilogram. Now we could also, at this point, we could also find H4 from the tables, because we were told that at exit from the first expansion stage, the vapor was dry saturated. Now we know that at that point, at point 4, we're at our intermediate pressure of 8 bar, and we're on the dry vapor line, which means that we could go to the tables at 8 bar again and read off the enthalpy of dry saturated steam, which is Hg. And if you do that, you'll see that the enthalpy is 2554. But we're going to check this on the chart anyway. And having checked that, then it remains for us to find enthalpy at point 6 and at point 8. And once we have these, then we can just go ahead and calculate our cycle performance. So if we go to our enthalpy chart, we're going to draw our expansion, initially our ideal expansion, through both stages of the turbine. So if we look at the high pressure stage, first of all, we know that at entry, that is point 3, to the high pressure turbine, we have a temperature of 450 degrees Celsius, and we have a pressure of 100 bar, which equates to 10,000 kilonewtons per meter squared on the chart here, or 10,000 kilopascals. So the point at which at 450 degrees Celsius and 10,000 kilonewtons per meter squared intersect is at this point here. if we draw a vertical line until we get to an intermediate pressure of 8 bar, so you'll see here's 8 bar equates to 800 kilonewton meter squared. So we have 500 here, 600, 700, 800. So we're down to this point here, which is our ideal condition at exit from the first expansion stage, 4 dash. If we do a similar line, this time through our low pressure turbine, again, this time we're told that our pressure was 8 bar and our temperature was 450. So where these two intersect, we're going to draw a vertical line until we come right the way down to a condenser pressure of 0.04 bar, or in terms of the chart, 4 kilonewtons per meter squared. So in which case we have this point here, which is 6 dash. All we do then is project across for 3, 4 dash, 5, and 6 dash. And using these, well, we already have 3 and 5. You can check these values against what you've taken from the tables. But using the values for 4 dash and 6 dash, as well as the 3 and 5, we're going to apply our equations for isentropic efficiency to find out what 4 is, or to check what 4 is, because we already have it from the tables, and also to calculate enthalpy at 0.6 at exit from the low pressure turbine. So first of all then, to check H4, then we're going to be using our enthalpies at 0.3 H3 and our H4 dash enthalpy. And you'll see from the chart above that H4 dash is approximately 2650 kilojoules per kilogram. Now it says there next page, of course it's just above. So if we apply an equation for isentropic efficiency of the turbine, then we have our actual output divided by the ideal output. So in terms of enthalpies, that's going to be H3 minus H4 for actual divided by H3 minus H4 dash for ideal. If we transpose that equation for H4, then we get H3 minus the turbine efficiency times H3 minus H4 dash. Now the actual steps in transposing this equation would be, first of all, take over the H3 minus H4 dash to the left hand side, in which case we have efficiency times H3 minus H4 dash, which means on the right hand side of an equation we're left with H3 minus H4. Now we want H4 expressed positively, so the only way to do that is to take the term H4 over to the left hand side of the equal sign, in which case now we have turbine efficiency times H3 minus H4 dash plus H4. If I want to then leave H4 by itself, I'm going to take everything else back to the right hand side, in which case I'm left with H3 on the right hand side, and I'm going to now subtract everything from the left hand side except H4, which is going to leave us with an equation of H3 minus turbine efficiency times H3 minus H4 dash. And if I just show that in its different steps, then we have our original equation here at point 1, where we have an efficiency of the turbine is equal to our actual over ideal output H3 minus H4 over H3 minus H4 dash. Take H3 minus H4 dash to the left hand side, in which case we have now efficiency times H3 minus H4 dash equals what's left on the right hand side, which is H3 minus H4. Take H4, the minus H4, to the left hand side, and it becomes positive. So we have all of this plus H4 now equals what's left, which is H3. And the last step now is to take everything from the left hand side, with the exception of H4, to the right hand side. So at the moment the sign of this whole expression here is positive. When I take it to the right hand side, it's going to become negative, in which case H4 is equal to H3 minus efficiency times our ideal change in enthalpy, H3 minus H4 dash. Remember, the only rule for transposition, or certainly the only rule that will get you by, is if a term changes side, it changes sign. Positive becomes negative, and vice versa. Multiplication becomes division, and vice versa. So inputting our enthalpy values then into that equation, we get an actual H4 of 2768.2 kilojoules per kilogram. And if we compare that to what we read from the tables, it was 2769, which is fine. If we go through a similar process in order to find H6, then apply an equation now as it applies to the second stage expansion, H5 minus H6 over H5 minus H6 dash. So we want to find H6. So do our transposition, input all of our enthalpy values, obviously, as well as using our isentropic efficiencies. It was 0.8 for both sections of the turbine, and we get our H6 now as 2532.2 kilojoules per kilogram. Now, for us to find the enthalpy at exit from the feed pump, we're given an isentropic efficiency, but we're not going to be using the chart to find H8 dash. If you cast your mind back to what the section on pumping on page 9, there's an equation there that stated that the exit enthalpy from the feed pump was equal to the input enthalpy plus VDP, the volume times the change in pressure. And that's the equation. If you look back to page 9, you'll see it at the top of page 9. This is the equation we're going to employ to find out the ideal enthalpy at exit from the feed pump, and we'll then apply our isentropic efficiency to the feed pump to find actual H8. So to find the ideal H8, we have an equation H8 dash, that is our ideal enthalpy at exit, equals our enthalpy at entry, H7. The notation obviously applies to the diagram for this example, plus our volume of our condensate, V7, times the change in pressure across the feed pump, which is going to be our boiler pressure minus our condenser pressure, P8 minus P7. So we already found H7 from the tables. It was 121 kilojoules per kilogram K. Our V7 is VF of the condensate, or liquid condensate, which we said the constant for that was going to be 0.001. Our change in pressure across the feed pump is our boiler pressure 100 bar minus our condenser pressure 0.04 bar. And to change that bar into kilonewtons per meter squared, or kilopascals, we multiply by 100. So in which case we now get our H8 dash as 131 kilojoules per kilogram. If we then apply our isentropic efficiency equation, thinking about ideal values, we're dealing with inputs this time rather than outputs, as we were for the turbine. Thinking about ideal values and actual values, the ideal input is going to be lower than the actual, so the actual goes in the bottom. So we have H8 dash minus H7 for ideal, divided by H8 minus H7 for actual. And again, transposing the equation for H8, we now get this expression here. Inputting our enthalpy values and our efficiency, we get the actual H8 as 135 roughly kilojoules per kilogram. Now you'll see these values are not hugely different. And as I said, very often the feed pump work is ignored completely, but it's there in this example, and we're given an isentropic efficiency, so that is how to calculate the exit enthalpy from the feed pump in these two stages. And in terms of that transposition, here's the steps taken. We start off with our original equation for efficiency of the feed pump, our ideal over actual. First step is to take H8 minus H7 over to the left-hand side, in which case we now have efficiency times H8 minus H7, which leaves us with H8 dash minus H7 on the right-hand side. Take the efficiency term over to the right-hand side, which becomes division, so we get this. And the last step is to take our negative H7 over to the right hand side, which becomes positive. So we now have H8 equals H8 dash minus H7 divided by the efficiency of the feed pump plus H7. So we now have we now have all of the enthalpies that we need to be able to calculate both the thermal efficiency and the specific steam consumption. So first of all, cycle efficiency, then it's the net work over the heat received, with the net work being, again, excuse me, the work done in both stages of expansion minus the work done on the feed pump, and that's going to be divided by the heat received, which is the heat received at the end of the superheater, and plus the heat received in the reheater tubes. So if we look at all of these terms, if you want to, you can just substitute the enthalpies straight into this equation here, or you can do as I've done here and just calculate them separately. So the work done in the heat pump, sorry, the work done in the high pressure turbine is H3 minus H4. The work done in the low pressure turbine is H5 minus H6. Again, you can be looking at the diagram just to confirm this. The work done in the feed pump is H8 minus H7. The heat received in the superheater by the superheat section is H3 minus H8. And the heat received in the reheat section is H5 minus H4. So inputting all of our enthalpy values and then putting these answers into our equation for cycle efficiency, we end up with an efficiency of 0.35 or 35%. Specific steam consumption, the equation is 3,600 divided by the net work. So 3,600 divided by the top line of our thermal efficiency equation, and we get 2.77 kilograms per kilowatt hour. The last part of the question asked us to state what the condition of the steam was at exit from the low pressure turbine. And to get that, if we look back to the chart and look at point 6, which is the actual condition at exit from the low pressure turbine, and we look at the lines of dryness fraction, which are these ones here. So we've got 0.9, 91, 92, 93, 94, 95, and so on. You'll see that it's on the line just before our dry saturated vapor line, in which case our dryness fraction on this line here is 0.99. So X is equal to 0.99.